Hello everyone, welcome to another video session class. So in today's class we will study about another name reaction, that is Oppenauer oxidation. So we know oxidation means addition of oxygen, simply classical concept, or loss of electron. Okay, loss of electron, that means if from any compound any loss of electron is happening, that is known as oxidation. Okay, so let us so this Oppenauer oxidation is having very widely used in the synthetic chemistry. So let us just see what is this Oppenauer oxidation. So Oppenauer oxidation is an organic reaction used to convert a primary or secondary alcohol, so from alcohol to ketone. Okay, you remember, from an alcohol, primary or secondary alcohol, so here it is secondary alcohol, so from primary or secondary alcohol to ketone. Okay, to a ketone using another excess ketone reagent such as acetone and an aluminium triisopropoxide catalyst. So this is aluminium triisopropoxide catalyst and another excess ketone, for example acetone. So that reaction is known as Oppenauer oxidation, you have to remember. So Oppenauer oxidation is named after Sir Robert Victor Oppenauer. So opposite reaction of Oppenauer oxidation is Marvin-Pondorf-Barlow reduction, or also known as MPB reduction. So you see, if you are just going from the reaction going from this side, that is alcohol with ketone, you are getting this alcohol is going to reduce to ketone. Okay, so that is known as Marvin-Pondorf-Barlow reduction. But if the alcohol is getting oxidized, that reaction is known as Oppenauer oxidation. So opposite reaction of Oppenauer oxidation is Marvin-Pondorf-Barlow reduction, or also known as NPB reduction. So the mechanism begins with the alcohol replacing one of the isopropoxide groups on the aluminum to generate isopropanol. So there is isopropanol, which is also known as sacrificial alcohol. So this sacrificial alcohol sacrificed itself to generate the ketone and your alcohol, okay, the final product. So in the reaction it will sacrifice itself, and at the end of the reaction it will regenerate itself. Acetone then coordinates to the aluminum complex and a rearrangement reaction occurs, which includes a hydride transfer from the alcohol to acetone. This process, which oxidizes the alcohol and reduces the acetone, results in the formation of the final ketone product and regeneration of the aluminum triisopropoxide catalyst. So let us see the mechanism. So it starts from here. You see, this is the structure known as aluminum triisopropoxide. Why it is propoxide? That means 3 carbon are there. One, this CH3, 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 CH, CH3, CH3, CH, CH3. So oxy is there. So trioxy, and prop means 3 carbon propoxide, aluminum triisopropoxide. So this reagent is known as aluminum triisopropoxide. So this alcohol, your primary or secondary alcohol, it will donate lone pair of electron to aluminum, and aluminum it will release this group, okay, CH3, CH, CH3O. So this group will liberate out. Okay, so here you see this is the group, and this OA, so you see OAl, okay, oxygen aluminum, this bond is formed. Next what will happen, this group will take, that is alkoxide group, okay, alkoxide group, or here it is propoxide group will abstract one hydrogen from here, so this will take up the hydrogen proton, and this will give its electron to the oxygen. So here you see CH3, CH, CH3, then OH. So this is going to the this is the next liberating alcohol. Okay, so in the next reaction what is happening here, our acetone is coming. Okay, acetone is coming to attack this aluminum. So here you see acetone, this oxygen will attack this aluminum. So here you see oxygen will attack this aluminum, and this CH, okay, this H will come here, okay, H will come here, okay. See what is happening, this bond is breaking, this H will remain here, okay, it will come to this one, this bond is breaking, okay, here this bond is breaking, so ultimately we are getting R1 R2 and here C double bond O. Okay, and this bond is breaking, ultimately this double bond will break and it will form, oxygen will form a bond with electron, so ultimately we are regaining the aluminum triisopropyl oxide. Okay, and at the end of the result we are getting this acetone along with this alcohol. So you just see the reaction, acetone along with this alcohol, correct, this acetone, and from this step we are getting the alcohol. So this is the mechanism of the Oppenauer oxidation. Next, the application. So the Oppenauer oxidation is also used in the synthesis of electrons from 1,4 and 1,5 diols. So from 1,4 1,5 diols, this aluminum butoxide or trioxybutoxide will be used as a reagent. So we are getting this product. So here oxidation is taking place. You see OH and here see OH, here OH and here C double bond O. So ultimately we are getting the oxidized product. Next, Oppenauer oxidation is also used to synthesize hormones like progesterone is prepared by the Oppenauer oxidation of pregnenolone. So this is pregnenolone. So if you do just Oppenauer oxidation reaction, it will give what? Progesterone. So this is the progesterone. So here you see OH, but in the next after completion of the reaction it is C double bond O. So we are getting one ketone. From the secondary alcohol we are getting the ketone in the presence of aluminum triisopropyl oxide. So this is also the Oppenauer oxidation reaction. So next is the slight variation. This means slight variation will be done in this Oppenauer oxidation reaction to synthesize the steroid derivative. For example, an efficient catalytic version of the Oppenauer oxidation which employs a ruthenium catalyst. So here it is ruthenium chloride has been developed for the oxidation of 5 unsaturated 3 beta hydroxysteroid to the corresponding 4 in 3 on derivatives. So here also slight modification is there in the catalyst, but ultimately we are getting the OH. From OH we are getting C double bond O. That means this is the reduction, okay, oxidation from OH to C double bond O. That is Oppenauer oxidation reduction. Next, as I have already mentioned, that is opposite of your Oppenauer oxidation is Marvin-Pondorf-Barley reduction. So you see MPB reduction is the reduction of aldehyde and ketones to their corresponding alcohol. So here you see from aldehyde to alcohols, okay, or ketones to alcohol, utilizing aluminum oxide catalysis in the presence of sacrificial alcohol. So sacrificial alcohol means this alcohol. This alcohol is sacrificial alcohol. So from ketone to OH, from C double bond O to OH, that means reduction is taking place. That's why it is known as MPB reduction. So MPB reduction was discovered by Marvin and Skint and separated by Barley in 1925. They found that the mixture of aluminum oxide and ethanol could reduce aldehyde to alcohol. So that is the reduction reaction generated. So I hope you have understood this Oppenauer oxidation along with this Marvin-Pondorf-Barley reduction. So I hope you have understood. Thank you.